So if you're looking at linear kinematics, displacement is the direction and the distance that something travels. What's the definition of the velocity of the object? Donald?
Rate of change of displacement.
Okay, so you got the rate of change of that displacement. And in the past, at standard grade, you said, well, the velocity is just the total displacement divided by the total time. And that was your average speed for a journey, and that was at standard grade. At higher, we then took that on a bit and said, well, it's actually, you could have velocity that could be a variable. That's how you're drawing velocity time graphs, where the velocity would change as you went through the journey. At advanced higher, we're taking a more mathematically correct definition of this and saying that it's the rate of change at a very small period in time, delta t. So if we take delta t here and the velocity increases by delta v, by delta s, the displacement goes on by delta s. The velocity is ds by dt. And you can do that for any period of time. You can say you can take it for a millisecond, a microsecond. In calculus, what happens to that period of change from maths when you're making a differential of something? What's the what can you do with that change? Exactly. We take it, it's called the limit as delta t tends to 0. So calculus is based on the fact that this becomes so small that it's not noticeable in terms of the bigger scheme of things, but there is a change involved there. So you have really that velocity is equal to dt, so it's equal to ds by dt. And that is the calculus definition of velocity. So what we're going to do is use that and then try and get equations for acceleration and displacement based on this. So if that's our calculus definition for velocity, what's the definition for acceleration? If the velocity is the rate of change of displacement, so if we were to draw a graph of something's displacement, say something was being dragged along the ground and its displacement was increasing s with t like that, what would you do to get the velocity at any point on that displacement time graph? Just looking at the graph. If that's the distance in the direction that the thing's been moved, if that's the time that it's been moved for, how would you get the velocity from that graph there? If you take the area, that would be effectively saying that we're taking the displacement multiplied by the time. And so distance times time doesn't give you that, does it? Velocity isn't so much you're not multiplying the two, you're not taking the area. We'll come back to what the area is in a moment. But how would you get the velocity from that graph? Right? Great. It is the gradient. So you take the gradient at any point, and that delta s divided by delta t, that's going to be the velocity as the gradient. And you can take the gradient at any point. That is what the velocity is. It's the rate of change at any point, and it's at that point because we're making that change, delta t, so small. And with various things, you've drawn velocity time graphs. For instance, if we roll a trolley down a slope here, if it was to roll a trolley down a slope, what would the velocity time graph look like for a trolley rolling down a slope? If we plot v there against t, Don? It would be a straight line through the origin, like that, because the velocity, that ds by dt, is constant, isn't it? Because there's nothing holding this back. The component of gravity, mg sine theta, that you know from higher, is pulling that thing down. That thing just keeps trundling down, keeps accelerating. Does it? It does.
There's a point where it can't accelerate.
There is, yeah. You get That's the theoretical, but in fact what happens is that it reaches this from standard grade. What was the name of that velocity that you can't really go any faster, whether you're skydiving or just taking a car down or a bike down Dromossie Brae? So you reach a terminal velocity. So this is one of the first bits where we're seeing it at advanced higher. The things aren't quite as simple as were first imagined in standard grade or at higher. We lived in a kind of ideal frictionless world in advanced higher with things that had perfectly linear changes in velocity, in other words, constant acceleration. The real world rarely has constant acceleration. Even a bit of chalk dropped vertically doesn't have constant acceleration. There's air resistance comes into play as soon as a bit of chalk gets dropped. So if we're going to be able to analyze these kind of motions, we need something a little bit more powerful than just the equations of motion. So that's where we're headed. Can we develop something using calculus which allows for these slight changes? Can we get something more powerful than equations of motion? Still, let's go back to what acceleration actually is. If the graph of velocity against time is there, even if we take it at a point on our air resistance graph there, our frictional resistance graph, velocity against time, how do you calculate the acceleration at any point on that graph? Kirsten, what would you do there to get acceleration for a velocity time graph? Yeah, okay. So the gradient is going to be delta v over delta t. So that's your acceleration, delta v over delta t. And it can be written as just, as the limit tends to 0, that would just become dv by dt. And if we wanted to express acceleration in terms of displacement, let's see who was listening on Tuesday, how could that be written in terms of displacement as a differential? Yeah, so how would it be written? Okay, so double differentiation d2s by dt squared. All it means is that we've differentiated displacement once, and then we're differentiating it again. So acceleration is d2s by dt squared. So we've got those two there. Now, just before, Kirsten was saying that you can take the area under a graph. If we had our velocity, you were talking about taking the area under that displacement graph. If you take the area under a velocity time graph, what's that going to give you? So here's our trolley running down. The velocity is increasing, reaching this terminal velocity, taking the gradient, dv by dt is the acceleration. If we take the area under that velocity time graph and start building up chunks of area underneath, what will the area under velocity time graph give you? Yeah, Aaron? Okay, so you get displacement. So going this way, you're getting the displacement as the area under a VT graph. In terms of calculus, what's that process of taking area, summing up a function? Now, this is going to give you a bit of thinking time. Madam Crusher? Yeah, what's the opposite direction there? Okay, Andrew, any ideas? Area under velocity time graph, what would that be? Yeah, even more thinking time. Madam Crusher? Not at the moment, no. She wasn't in. Yeah, I don't think she's in on Tuesday either, so it might be worth chasing it. Yeah. Okay, thanks, bye. Everybody know about Andrea? She wasn't in on Tuesday. No, okay. Right, the Andrew. Area under the velocity time graph? No? Well, it's giving us displacement. If you take the gradient of a graph, you're getting the differential. You're differentiating the function. So if you take the area under the graph, Aaron, you're integrating it. So really, displacement is the integral of velocity with respect to time. So you're summing up all these little strips of area underneath the velocity time, and you're adding them all up. Does that ring any bells from higher maths? Thank you, Kirsten, because it does. You've done it. Okay, so we can go two ways from velocity. You can integrate to give you displacement. You can differentiate to get acceleration. If you were to take acceleration graph, say if you had an acceleration graph, which for this function, you'd have a high acceleration initially, and then the acceleration would get less and less and less. So if you had acceleration against time, how could you build up that velocity time graph from an acceleration time graph? Oh. Okay. So if I took strips of this graph and integrated to say that v is equal to the integral of acceleration with respect to time, I would end up making up that graph there just because the velocity increases. We get big increases in area to start off with here, and then the actual increases in area that we're building up towards the tail end here are very small. So to get velocity from acceleration, you're integrating. And to get displacement from velocity, again, you're integrating. So you really have a sequence there. Displacement to velocity, you differentiate. Velocity to acceleration, you differentiate. Acceleration to velocity, integrate. And velocity to displacement, again, you're integrating. So you can go both ways there, both because they're both a rate of change with respect to time. Okay, time to get you to do some thinking now with, can we get the equations of motion? So what we're after as a bottom line is going to be S equals ut plus a half at squared. We're after v squared equals u squared plus 2as, and v equals u plus at. That's where we're headed, but we're not going to do it with looking at a graph. We're going to think of it purely in terms of differential calculus. So the starting point is just that A is equal to d2s by dt squared. Which one of those there could I pick off first, just by one integration? Acceleration. So we're going to integrate acceleration with respect to time. Now, for this one here, we're just going to assume that acceleration is constant. I should have said that before. So we're using constant acceleration. So we're accelerating acceleration with respect to time. If you integrate acceleration, then it's just going to be the two things you remember for integration. One, you raise the power. And two, divide by the new power. So if we've got a t to the power 0 dt, are you happy with why I've written t to the power 0 there? Because that's just a constant, and we're integrating it with respect to time. So because t to the power 0 is equal to 1, it's effectively a times t to the power 0 dt. If you integrate a constant, you're effectively raising the power t to the 0. You're putting it up one power, so we've got a times t to the power 1. T to the power 1 is just t. Dividing it by the new power is now 1, divided by 1, plus that constant. Okay, so all we're doing is integrating constant acceleration with respect to time. And so if you integrate a constant with respect to t, it's just going to be a times t. That is, because we've integrated velocity, that's now going to give us velocity. So v is equal to at plus a constant. Because at t equals 0, v v is equal to u, we've got v equals u plus at. Okay, that I hope is a clearer description of it. Thanks, Donald. The first one wasn't particularly clear, but I'm perfectly willing to answer questions on that one now.
How did you get that integral of all that jazz on the left side is v?
Because that's what we were saying before, that acceleration is dv by dt. So the acceleration there, if you integrate acceleration, you'll get velocity. Yeah. So that's our first equation of motion. That's taken half the board. We've still got 2 to go. The next one follows a similar process because we know that v is equal to ds by dt. Can we get the second one by a similar process? So we're saying that velocity is the differential of displacement with respect to time is equal to at plus u. I'm going to give you a minute now to think what you could do with that. Would it work? Could we go through a similar process to get to our second equation of motion? So we're going to take this function here, which is v equals u plus at, just written a slightly different way here, and going to then integrate this one. So because displacement is the integral of ds by dt with respect to time, so if we integrate that, we should be getting s. So it's the integral of at plus u with respect to time. And you've all, by yourself, said, well, at, raise the power of t, we get at squared. Divide by that new power, that's dividing by 2, plus u. It's just a constant in that line, so integrating with respect to time, you're increasing the power of t to the power 1, dividing by 1, so it's this left is ut. And you were all very happy with that, but you had, to a person, forgotten one little thing. Is there a constant? So at time t equals 0, what's s equal to? Yeah, we generally start things at a 0 point. We say that when something's starting to move, when the stopwatch starts, we assume that we're measuring the distance from that point. So although you've got a constant, s is equal to 0, so we've got that s equals half at squared plus ut, which is our second equation of motion. In between there and there, we somehow need to get v squared equals u squared plus 2as. And the procedure for that is very similar to the procedure that you used last year, because you've got 2 equations, one with vu, a, and t. This one's got s, u, t, and a in it. What you want is v squared equals u squared plus 2as. We want to get rid of the t in that one there. So can we get rid of t? The easiest way is to say, well, from this equation here, t is equal to v minus u over a. Replace that t into this equation here and here, and then it usually takes 6th-year students under 5 minutes to do all the algebra to get from that substitution by doing things like expanding brackets, collecting terms, dividing by what's its well, all that sort of shenanigans to get to that one there. Maybe do it in the back of your notes, Dora, so it doesn't mess up your real notes unless you're feeling really confident. That's really going to be the 3 steps that I'm going to go through. Multiplying through by 2a, expanding out the brackets, and then collecting terms. So see if you can follow that to end up with the final line. Let's just take it through. So we've got, putting in v minus u over a wherever there's a t, we've got s equals half of a times v minus u over a all squared plus u times v minus u divided by a there. First thing I did mention to do is to multiply through, get everything on top. The two things that are on the bottom at the moment are 2 and a. So I've got 2a times s equals a squared, v minus u squared on top, a squared on the bottom. That cancels. Plus u times a, because there's only one a on the bottom. Oh, no, sorry. Just one a on the bottom, one a on the top there. So it's 2u times v minus u. So that's all I've done there, multiplied through by 2 times a. So this is looking promising. I've got 2as on that side. Over here, v minus u squared, v squared minus 2uv plus u squared plus, expanding this bracket out, 2uv minus 2u squared. I've got, the nice bit is that the 2uv minus plus 2uv cancels. I've got v squared there. I've got a plus u squared. I've got a minus u squared. So we've got v squared minus u squared equals 2as. Rearrange that, and you get v squared equals u squared plus 2as by taking the minus u squared over on the other side. That is your third equation of motion. Now, some of you are thinking, well, big deal. We've used differential calculus and got exactly the same point that we got with using velocity time graphs last year for constant acceleration, because these three equations of motion still only apply for constant acceleration. The good thing is, and this is the thing we'll be going on to next time, is how do we then treat motions with varying acceleration? You can do the same thing. You might have an acceleration which isn't constant. You might have an acceleration that depends on time, but again, you can integrate it. You might have then that can be integrated to give you velocity and then to give you displacement. Even though the acceleration depends on the time, that's what we're going to go on to next time.